Okay, turning a corner here. This is the foundation. Don't look here yet. This is the foundation of the rest of the quantitative stuff we're going to do in the course this term. There's a lot of this, but it's the foundation for the rest of it. And I'm just going to take a moment to recap where we've been, where we're headed, and then introduce how this really simple equation that you're beating your brains out to try to remember from grade school, how it fits in to where we move now. We've done statistical significance test, chi-square, for relationships between nominal and ordinal variables. We've done measures of association between two nominal variables, and we're going to move on now and we're going to develop a measure of association for two variables that are at the interval or ratio level. Technically, less technically, you can use the measure of association we're going to develop in this series of videos for ordinal or dichotomous variables. This is a very powerful tool called regression. I was looking at the title and I was kind of laughing, Introduction to Regression, kind of like we're going to go backwards. Regression is the name given to a type of statistical analysis that will, again, constitute the foundation of everything that we do for the rest of the term of a quantitative nature. We finish up with ethics, but that's lecture only and in person. Quickly, to the board. I put this up routinely, people immediately recognize it, and some people have trouble remembering what it is without the lines. When I show the lines, immediately people remember that this is the formula for a straight line, a formula that you were taught on a piece of graph paper in probably the 7th grade, maybe 6th. I'm guessing, I don't know what grade. Even for you a long time ago. So I'm sort of reach back into the memory bank and retrieve whenever it was that your school teacher had you working with graph paper and drawing, moving this far on the x-axis and this far on the y-axis, and introducing the formula for a straight line defining terms. Y is the score on the y-axis, the x is the score on the x-axis, this way. M, remember, is the slope, and B is the intercept. The point at which the line crosses, the intercept is the point at which the line crosses the y-axis. This is easy stuff. There are only two, aside from the y and the x, there are only two parameters in the equation of interest, the slope and the intercept. So slope of that line, you're looking right there, and the point at which it crosses, we can imagine it keeping going, maybe. That's the intercept. You remember all of that. You remember that the slope is the unit change in y that results from a 1 unit positive change in x. So if you move this way, you move that, m units that way, and you remember all of this. Now look here, fun. When I've taught this course before and I put this equation on the board first, as opposed to this one, I have a riot on my hands. Oh my God. So we're going to do something extraordinarily complicated here. No, all I've done is translate exactly this formula for a straight line into the syntax and notation, the beginning syntax and notation of people who use regression analysis, which soon is going to be you. So I've renamed BA, and you're going, why do you do this? I didn't invent notation conventions. I didn't invent them, so follow along. I insist. All I've done is taken B and renamed it A. So A is the intercept. And I've taken M and renamed it B. So B is the slope. There's nothing here except an arithmetic translation. And a change in notation. It is customary to denote the intercept of a regression line when you're doing statistical analysis with an A and the slope, what we'll call henceforth the regression coefficient associated with X, to denote it as D. So I got 3 lines up here. I'm going to get rid of 2 of them momentarily, but not before reminding you what's going on here. I'm going to go ahead and get rid of formula for a straight line, as you learned it in grade school, because we're going to henceforth remember it and dig into it in this way. So y equals a plus bx, the intercept plus the slope times x. So I have 3 lines up here. The first and most simple line is this one, right? And just a reminder, now if you probably, some of you are thinking about going ahead, for notation reasons I suggest that you don't. On the other hand, what I'm describing here and what I'm teaching here is fantastically simplistic. So if you feel the urge to go ahead, fight it for a moment and stay with me because I'm about to make a transition, but not until I remind those who took math in 6th or 7th grade and flushed it out of their brains what was in their head back when they were children. Okay, so the intercept of this line is what? Yes, you said it. It crosses at 0. So in this case, a equals 0, and the slope of this line is 1. And you can see that readily because you move up 1 unit on x, you move up 1 on y. Move up 1 more unit, you move 1 more unit. 2 to 2, 2 to 2, 2 to 2. When you were young, you were drawing points in the Cartesian plane. Try to remember that. Even at home, do it if you have to remind yourself of where you used to be. So I've got another line that's parallel to it right here. These lines are parallel, and that means they have the same slope. So as x increases 1 unit, once again, y is going to increase 1 unit. The slope of this line is 1. The slope of this line is 1 also. So we'll call this line 1 and this line L sub I. Should we do that? We'll subscript our little lines. And so this one right here. Both of these have a slope of 1. The only difference in terms of the intercept, the y-intercept over here is 4, right? And then we've got another one, a third line here, and once more it crosses the y-axis at 0, so its slope is going to be this. We call this line 3, right? Line 3 is going to have an intercept again of 0. Slope's different though, right? So you move 1 and I jump up 2. And I move 4 units and I'm all the way to 8. This line has a slope of 2. Move 1 unit on x, bump up 2 units on y. The unit change on x, a 1 unit positive change on x produces a slope unit change on y. So this is 2. And there's your introductory sort of 6th grade math presentation, the foundations of a very powerful idea. I'm going to get rid of this. Leave nothing but the line. That one, recall, intercept is 4, the slope is 1, and I'm going to now mess it up. So I'm going to subscript sub I and x and y in the same way. In the same way that we have when we introduce notation. So I'm looking at, because I should have put my students back up here, whose names start with a J. So we're looking at values on x across individuals, or some unit of analysis, and we'll call it students. And I'm going to do the same thing for y. And we're not going to have a straight line at first. what we're going to have is a scatter. So imagine now that we're not going 1 unit, but there's a 0 to 100, or up here 90. Here's 0 to 100. And so we've got a continuous interval, and there we can plot points. And you probably did this too when you were in 7th grade. And you fit a line in between the points. And that's what we do here. Naturally, none of the individual points are going to fit on the line, but they're going to scatter around it sometimes if there is a particular type of relationship between a ratio or interval level y and a ratio or interval level x. So imagine we are plotting GPA and grade on a test, and somehow I scaled GPA to be of 0 to 100, and got 0 to 100 on the test. So I believed that GPA measured achievement prior to coming to the classroom, and then so it's going to be a predictor of how well you do, but it's not going to be a perfect predictor. That is, all of the points are not going to fall on the line, they're going to fall around it, and it's up to you to fit a line here. Now, but whereas before we had only a y, an a, and a b, and an x, now we've got something else up here. We've got space between the actual observations, the points, and a hypothetical point for each observation that falls directly on the line. So they're going to add this here and call that the error term. This is it. This is the foundation of the rest of the quantitative work in the course. This is what's known as, write this down, a bivariate regression equation. Bivariate referring to the fact that there's only one x and only one y, sum total of 2 variables involved in this analysis. It's a bivariate regression model. And the task ahead is going to be to learn how to translate this, which is a sort of idea with sample data, into the notion of estimating population parameters. So that's the next video, is about essentially estimating where the line fits, and talking about using these things, A and B, the estimated intercept and the estimated slope, to make inferences about population parameters, coming up in video 2.